We are getting real deep in it today. We are going to talk about the physics of vibration and how those relate to drum shells. So when we talk about vibration, objects will vibrate in many different modes. And that means basically just a different pattern that something vibrates in at a certain frequency. So if we look at something really simple like a guitar string, we still have several modes in which they vibrate. So a guitar string, as we know, is just a string tension between 2 points. Now the fundamental note of a guitar string is going to be the lowest note that it vibrates at, and that's going to be basically where the string oscillates in an arc one way and oscillates in an arc the opposite way. So it goes back and forth between those two spots. And that is the first mode of vibration and the fundamental lowest note that it can produce. Now at the same time, a guitar string is also going to resonate at the second mode or a harmonic of that first mode. So this mode would be an octave above this mode, where instead of one continuous arc, you get a waveform where basically you have two arcs going back and forth opposite each other. And this is going to vibrate at a frequency twice as fast as this one. Now you're also going to have more. So these basically just keep dividing the string into different harmonics, and those are each different modes. So we would also have a mode of vibration where the string is basically divided into thirds. Now this is going to vibrate at a higher pitch than this, and this vibrates at a higher pitch than this. And there's also a harmonic in which the string vibrates back and forth this way. So all of these create different notes, and all of them are present when you're playing a guitar string. They are all vibrating, they're all happening simultaneously, and each contributes a different harmonic to the overall sound. For example, all right, the lowest note this string can make, in this case, is an E, and it's just basically one arc going back and forth. If I want to get this harmonic, I damp the string at basically right in the middle between the bridge and the nut, and that's one octave higher, and what's happening is this right here. I can make this one happen too by putting a finger and dampening a third down the string. Here that's a higher pitch, and I can also do it right here. That's this harmonic. So all of these produce different notes, this one being an octave above that one. All right, so that's a guitar string. That's about as simple as you can get in terms of modes. Now I personally started to learn about modes of vibration when I was working with marimba tuners. Back in a previous job, designed marimba parts, and we worked with the tuners at the factory, and man, it just blew my mind when they explained how they tune a marimba bar. So this is a 3D object, a whole lot more complex than what you get with a guitar string. So a marimba bar is typically going to have a nice cutout like this and is suspended on strings at both ends. These are the nodes, or basically points where they don't want that fundamental to vibrate. So just to simplify, we're going to get rid of this and just make it kind of a rectangle. Makes it much easier to show what's going on. So the first fundamental mode of vibration that you're going to get in a marimba bar is where the bar arcs basically like this, and then it's going to rebound the opposite direction like that. I recognize that's a little scribbly, but you get the idea. That's the fundamental. That's the lowest note that marimba bar can take. But you're also going to get, if you're looking at it from the side, all of the same harmonics that we saw with the string. Kind of, I mean, obviously this is a very exaggerated form, but it's going to go like this and then rebound to this type of shape. So there are any number of harmonics that can happen along that axis and length of the bar. But you can also look at the bar from the top, and you can get harmonics where the bar oscillates this way and that way. Then there are harmonic modes where the bar actually twists, and so the bar is going to oscillate back and forth like this. I don't even know how to draw that, but it happens. And when they're tuning marimba bars, they can actually tune by manipulating and cutting away wood. They tune these different harmonics so they hit specific notes with intervals that are pleasing to the ear. It's awesome, and the science behind it is super cool. So that's marimba bars, but we're all drummers here, and we want to talk about drums. So drum heads vibrate in these different modes, and that is a really cool topic, and we're going to get real far into that in a future video. But just to say, it's a 3D version of a guitar string, and it does all the same sorts of things, but with a whole nother dimension added. So stay tuned for that video. It's really cool. But in the meantime, we're going to talk about drum shells, how they vibrate, and how that affects the way we design and build drum shells, or should design and build drum shells. All right, so how does a drum shell vibrate? You know, this is really important. We talk so much about how we lay up the plies and the woods that we use and all these things that relate to how the drum sounds. And when it all comes down to it, what we're really talking about is how is that drum shell vibrating? Now, when you have a shape like a drum shell, there are a few modes that these can vibrate in. The first one, which you'll often see people tap a shell like this, that displays the fundamental frequency of the shell. That's the lowest note that shell can vibrate at. So what's really happening there, if you were to look at the shell from the top, that's in its resting state. When you hit that shell, you're essentially deforming it ever so slightly into an oval. You hit here, it flattens out that shell, and then that shell is going to rebound into an oval this way. This is obviously exaggerated, but this is essentially what's happening. And you're going to go back and forth in both dimensions, and you're going to get that vibration. So the lowest note, lowest frequency. However, when we actually put together a drum, you put a head over this, you put a hoop over this, you tighten it all down. This doesn't happen when it's assembled as a drum. This fundamental note is not functional. It's not a functional mode when we build a drum. So this is something that we don't design to. It doesn't matter. Anyone who says, you know, that's the note of the shell is just wrong. We know that that circumference is pretty well rigid. When we put that tensioned head on it, it's not moving like that. What is moving is the rest of that shell along its length. So we get modes of vibration where the shell may flex this way, and then oscillate back the opposite way. You can imagine the shell just kind of shifting back and forth like that, and basically vibrating down its length. And then there's also harmonics of that motion where we get more of a wave. The shell is basically shifting this way and that. that shells actually vibrate when we play a drum. And when we design a drum shell, we want to make it so the drum shell can vibrate this way. So that means we try to make a shell stiff in its circumference to hold a head, and we try to make it flexible along the length of the shell such that it's easier to vibrate that way. Now, you can hear these different modes of vibration with tapping. So this is not a particularly valid method of hearing a drum shell and what it's going to do. That's the fundamental of the just loose drum shell hanging out, but once you assemble it in a drum, again, that's kind of dead. So, how do you hear those harmonics? So, to get this mode of vibration here, we're going to suspend the shell right in the middle, and we're going to tap on the edge so that we're getting that oscillation back and forth this way. That is a different pitch than this. We can also hear a harmonic when we support one end of the shell and tap opposite that. So we have 3 different harmonics we can test in a shell this way. So I think an understanding of the different modes of vibration of a shell really gives you a better understanding of, how do you want your shell to flex? What kind of design features do we put in it to get the sound that we want? For example, if you think of a vintage 3-ply shell with a reinforcement ring, that reinforcement ring reinforces the circumference. Again, we're not really moving that circumference. We're moving the shell along its length. So you have a real thin shell between the ends, and the ends are reinforced with a reinforcement hoop. That's why those drums sound warm and open and resonant, is because they have basically a thin shell along the length, very flexible shell end to end, but around the circumference it's stiff. The indie shells, for example, these are our flex-tuned maple shells, designed with much more horizontal grain ply than vertical ply. We have thicker horizontal grain plies, thinner vertical plies, and that basically gives the same effect. It's really stiff in its circumference, but it's softer along its length, and it's reducing mass, which is another huge piece that we'll get into in future videos. But it's a really important factor when you're considering how a drum shell is designed. So hopefully understanding these different modes that the shells vibrate in can help you understand how drum shells are designed, why they sound the way that they do, and helps you select drums that give you the effect that you're looking for in the future. I really appreciate you watching this Drum Nerd Lab video. We've got a lot more great content like this coming, so please make sure you subscribe to these videos and stay tuned.